Hello, welcome to the NMR spectroscopy lecture number 6. In this lecture, we will study the carbon-13 NMR and how to interpret it. So, while studying carbon-13 NMR spectrum, there are two types of spectrum that are commonly used. It is off resonance. Two types of spectrum of resonance, decoupled spectrum, and other is broadband decoupling. Broadband decoupling. So what is the off resonance decoupled spectrum? In the off resonance decoupled spectrum, splitting is visible. So we can see the splitting in the off resonance decoupled spectrum, but in the broadband decoupling, splitting is not visible. So there is a no splitting. Every peak will be singlet. No splitting. So in the off resonance decoupled spectrum, all the protons that are attached to the carbon will show the splitting. Like this is a carbon, and there is a 1, 2, 3 types of 3 proton, but they are of one type. But in the splitting, there will be a quartet according to the n+1 rule. There are 3 protons, so n is 3 plus 1. As we have studied in the splitting of the proton NMR, we always have to add 1. This is a multiplicity. So this will give us a quartet. But on the same molecule, we perform broadband decoupling, then there will be a singlet in the spectrum. There will be no quartet. So in the off resonance decoupled, there is a more information, because we can determine from the spectrum that how many protons are attached to the carbon. So there is a more information in the off resonance decoupled spectrum. But in the broadband decoupling, there is a loss of information. So why we do broadband decoupling? We do broadband decoupling because to study the off resonance decoupled spectrum is complex. To study broadband off resonance decoupled spectrum is complex, while studying broadband decoupling is simple. So in order to prevent to study the complicated spectrum, we use broadband decoupling, in which all the peaks will be singlet. So let's move to the shift. These are the chemical shifts for the carbon-13 nuclei. As you have studied about the chemical shift for proton nuclei. For the proton nuclei, chemical shift started from 0 to almost 12, but here 0 to 240. 0 to 240. So these are the chemical shifts for the carbon-13 nuclei. So whenever you have to interpret the carbon-13 spectrum, you need to look at this table, because you can't remember all the shift ranges. So if your compound or molecule has this CO carbonyl, then it will in the range of 200 to 220. It is higher than all the other carbons. So whenever you find a shift value near to 210 or 220, you should you are sure that there is a carbonyl carbon. So we are looking at the carbon because this is a carbon-13 NMR spectrum. We are not interested in the proton, we are interested in the carbon. So here, like in the CH3, CH2, CH, and this is the quaternary carbon, so they will lie in 0 to 100, almost 10. And if the carbon is attached to the fluorine, it will lie around 65 to 110, because fluorine is electronegative than the chlorine. If the carbon is attached to the aromatic ring, then it will lie in this range. So from this table you can just assume that where my carbon will fall. What is the range of the carbon? What is the range of the signal in the NMR spectrum? So I suggest that you always need this table while doing the interpretation of the carbon-13 NMR spectrum. So this is a off resonance decoupled spectrum. I have already told that in the off resonance decoupled spectrum there is a splitting. So first of all you have to look at the structure of the one. This is the structure. So let me change my pen color. Okay, this one is. So in order to interpret it, first we have to write it in a simple way, like in that way. C H H Cl CCl. Okay, so whenever you have to interpret the carbon-13 NMR spectrum, first of all you have to open your structure, because when you will open your structure you will know that how many type of carbon are there and how many protons are attached to them. So there are 2 protons attached to this carbon. You can number your carbon A, B, C, D. So there is already a spectrum. They already numbered that carbon. So we can find that which one carbon represents C, which one carbon represent B, which one carbon represent A. So the first signal is the tetramethylsilane signal. So this is our reference compound, so its signal will always be at 0. If you find any signal at 0, so you should know that this is our reference compound, so no worry about this. So this is a compound. We are going to determine the NMR spectrum of this compound. So first of all, let's look at this carbon. This carbon is attached to the 2 proton. So in the carbon-13 NMR spectrum, you should know that we will not count the splitting of the neighboring carbon protons. So if there is a proton in the place of the chlorine, then we will not count that in the splitting of that carbon. So we will only include the splitting of that protons that are attached to that carbon. Okay, in order to determine the splitting of that carbon, so there are 2 proton attached, so 2 plus 1 is equal to 3. So it will be go to the triplet. So this is a triplet in our spectrum C. So this carbon is C. So let's go to this carbon. This carbon is attached to the 2 chlorine. So chloride molecule, sorry, 2 chloride, this carbon is attached to the 2 chloride. So there are also a proton in the neighboring carbon, so we will not count that proton, we will only count proton that are directly attached to the carbon. So there is no proton directly attached to this carbon, so what will happen? So it will give us a singlet. So this is a B type of carbon, this one, so it will give us a singlet. This will give us a triplet. Okay, so last, this is the third number of the carbon. This carbon is attached to the 3 type of protons. So when I say 3 type of proton, in the proton spectrum we count that this is only a single type of the protons are attached, but here I would prefer that there are 3 types, like these all 3 proton will attach in the splitting, will count in the splitting, like 3 proton, 3 plus 1, so 4. So it will give us a quartet. This is a quartet signal, so this is a type of carbon, so it will give us a quartet. So they have already solved this here, so I just open the structure and it is more easy for you to open the structure and then start finding this. So in the off resonance decoupled spectrum you can get the splitting, and what is the benefit of splitting is that you can find that how many protons are attached to the carbon. If you are looking at the carbon C, so in the spectrum you can know that how many protons are attached to the carbon, because when you do the NMR spectrum, if there is an unknown molecule, you don't know about that molecule, so it is very beneficial to do off resonance decoupled spectrum. So this is a decoupled spectrum, this is a proton decoupling. So how we write proton decoupling? Like this is a carbon-13, we are decoupling proton. So this is a proton decoupled carbon-13 NMR spectrum. Here is written that all lines simplify to singlets, including the absorption for tetramethylsilane. So tetramethylsilane signal will be singlet in the carbon-13 decoupled spectrum. Not off resonance decoupled, but it is a broadband decoupling. So here the shift values will remain the same, like this is the A type of carbon. So A type of carbon, it is around 33. So here A type of carbon, it is around 33. So all the shift values will remain the same in both types of the spectrum, in the off resonance decoupling or broadband decoupling. But the difference is that all the peaks will be turned to the singlet. So there is no complexity in the decoupled spectrum. All the peaks are the singlet. So this is the spectrum which we get to just for the easiness, just to avoid the complexity. So next example is about the para-ethoxybenzaldehyde. Para-ethoxybenzaldehyde have different types of carbon, many different types of carbon. So we have to look at symmetry, like this C2, C6 and C3, C5 are the same type of carbon. If there are same type of carbon, so there will be signal for those carbons, like C3, C5 are the same type. This is C3, this is C5, so their signals will be 1. Like this is a signal of the C3, C5. So C2 C6 are same type, C2 and C6, so their signal will be this one, only one signal. If there are equivalent carbons, same type of carbons, so you can check the symmetry by cross like this. So these are the same, these are the same. So this carbon is different than this carbon. So why these are different? Because this carbon attached to the oxygen, this carbon is attached to the next carbon. Okay, so you have to look that these two types of carbon are two different types of carbon. So this is carbon number 8 and carbon number 9, so these are also different types of carbon. So first of all, you have to find how many different types of carbons in our structure. So after finding that, you have to look at that what type of spectrum. It is the broadband decoupling, so all the peaks will be similar. So CHO, C double bond O, single bond H, this is okay. So this is an aldehyde. You can go back to the spectrum and just look at that what will be the signal of this type of the carbon. So this signal is about the 200. So if you don't know the molecule, you can look at the spectrum and just you can assume that okay, at the 200 there is a aldehyde carbon, so you can write in your structure that there is an aldehyde carbon. So TMS signal is the singlet. We have already studied that TMS will be singlet in the broadband decoupling. So we are not interested in TMS, we are interested in the carbons. So carbon number 8 is here around I think it is around the 70. So you can go back to the table and you can assume that where my shifts will fall. This is an off resonance decoupled spectrum of the same molecule that we have. This one, para-ethoxybenzaldehyde. In the off resonance decoupled, all the peaks will split. So there is a splitting. There would be splitting for every type of carbon attached. Like this is a aldehyde carbon. So there is a single proton attached to this. So for the single proton is attached, so it will give us a doublet. So you can check all the carbons and how many proton are attached to it. You can look at the spectrum and you can just tell that. So there are two protons, so it will give a triplet. If there are 3 proton attached to carbon, it will give us a quartet. So it is very simple when you are used to this. You will practice a lot. So this is very simple. So thank you for watching the video. If you like the video, please subscribe my channel.